All right, welcome back. In this video, we're going to start looking at chapter 20 of WADE, which is about carboxylic acids. And today's video is one of today's videos, we're going to look at the acidity of carboxylic acids. And I'm probably going to do two videos on this. In this first video, we're going to look at the acid dissociation equilibrium for carboxylic acids, and in the second video we'll look at some trends in acidity of carboxylic acids. So carboxylic acids occur in amino acids. They're one of the functional groups in amino acids, and so their pKa's are important. That's one of the reasons. And so if we look at a general carboxylic acid, it's going to have this structure. So it's a carbonyl compound with an alkyl group attached to one side and an OH group attached to the other side. Okay, and any acid dissociation equilibrium, or when we're trying to figure out Ka's and pKa's, we're reacting a molecule with water. Okay. And then a Bronsted acid-base reaction can occur. We're transferring a proton onto that water. All right, and we're going to make a carboxylate. Plus H3O plus. Okay, and so we got carboxylic acid, carboxylic acid going to form a carboxylate. All right, the equilibrium, the acid dissociation constant for this, K sub A, is going to equal the concentration of our CO2 minus times the concentration of H3O plus. So those are our two products, and that's going to be divided by the concentration of our CO2H. Okay. We usually don't include the concentration of water in an acid dissociation constant because it's a solvent or it's in excess, its concentration stays relatively constant. Okay. We could also write, we can take this and make a pKa value. So the pKa is going to equal the negative log of the Ka. Okay. So the Ka values range in 10 to the negative third to 10 to the negative fifth for carboxylic acids, and therefore the pKa is going to equal 3 to 5. Okay. A typical carboxylic acid, acetic acid, where R is a methyl group, CH3, is going to have a pKa of 4.7. Okay, so that's good to keep in mind. Typical carboxylic acid has a pKa of 3 to 5. And we can compare this to alcohols. So I'm going to do that. And then we're going to look at a little bit at why they have different Ka values. So carboxylic acid, I'm going to say pKa is about equal to 3 to 5. Okay. If we do this for an alcohol, use black for an alcohol. alcohol, if you recall, is an OH attached directly to an alkyl group. And its acid dissociation equilibrium will look like this. Alcohol plus water goes to form the alkoxide plus H3O plus. Okay, and here the pKa is about equal to 15 to 16. Okay, so we've got a difference of at least 10 pKa units here. And that's quite a big difference. So that's, if we're looking at the Ka values, that's 10 to the 10th power difference in the equilibrium value, acid dissociation equilibrium constant. Okay, and that large difference all has to do with this structure. Okay, with the alkoxide, we've got a negative charge here that's localized, that's restricted to that oxygen. However, with the carboxylate, we can draw a resonance form of this, where we can delocalize this pair of electrons to form a pi bond here. And we have this second resonance form of that. Okay? And so, because whenever we can delocalize a negative charge across multiple atoms, that makes that more stable. So this carboxylate, this anion, is more stable than this one. And that results in this being more acidic than this. Okay. A good way to kind of illustrate this is with an energy diagram. So I'm going to do that next. All right. So on the y-axis in an energy diagram, we've got energy. And on the x-axis here, we're going to have the reaction coordinate. So going from reactants to products in these acid-base reactions. Okay. And I'm going to use, I'll use blue for the carboxylate. And I'll use green for the alcohol. Okay. Now, in the neutral forms, the alcohol, we're going to assume that the alcohol and the carboxylate have about the same energy because there's no charge that's unstable that has to be delocalized. So, so I'm going to erase things with my finger. So we're going to say that the alcohol plus water has about the same energy as the carboxylic acid plus water. Okay. However, if we look at the products of these acid-base reactions, with the alkoxide, okay, plus H3O plus, this cannot be delocalized, so it's fairly high in energy relative to the carboxylate. Okay, plus H3O plus. All right. So here's kind of the hill we climb to get to these products versus a higher hill that we climb to get to the alkoxide. Okay. Since the carboxylate is more stable than the alkoxide, the energy difference between reactants and products for the carboxylic acid is smaller than the energy difference for the alcohol and the alkoxide. And so what that means is this is more acidic, the carboxylic acid is more acidic, and it has a lower pKa value. So pKa of 3 to 5 versus a pKa of about 15, 16, or 18 for some alcohols. All right, and that concludes our first lecture on acidity, carboxylic acids. In the next one, we're going to look at, we're going to review some trends of acidity, specifically in the context of carboxylic acids. Thanks for watching.